Well, welcome back everyone. Mrs. Hanson here again. We're picking up our lessons in chapter 12 on the alkanes, and they are, we're at top of page 7 in our notes already. And this particular section continues talking about alkanes, and we're picking up with talking about bond rotation, skeletal structures for acyclic alkanes. And I recall saying earlier in the lesson about freedom to rotate on any single bond. So keep in mind as you're investigating whether or not compounds are indeed the same or different, don't let the rotation of the single bond bother you. So the rotation can occur around carbon to carbon single bonds. And notice that it's the location really of the two carbons in a row here where I'm noticing that I can take this sigma bond, this single bond, which is called a sigma bond, and I have freedom to completely rotate that in space and not changing the identity of the molecule. So as long as the bonds do not break, they are free to rotate and still keep the molecule the same. We know that the most stable arrangement for a molecule avoids crowding, and therefore a zigzag arrangement of the atoms is the most stable configuration. So notice that when I take 1, 2, 3, 4 carbons, so a butane, and I place them in that zigzag fashion, I am maximizing bond angles. Whereas if I were to twist this bond between carbon 2 and carbon 3, forcing the ends to come up near together so that I end up with a line structure kind of pointing up at both ends, I have what is called steric hindrance. In other words, there's too much crowding going on between carbon 1 and carbon 4, and that is really not the preferred rotation. So give the atoms as much space as you can as you begin drawing out your condensed formulas. So notice, just as an example of what we're saying, these are all very valid structures for pentane since single bonds can rotate. They are not isomers of each other, but the exact same compound. All of the atoms are bonded in the same order. If it's in the most stable configuration with the zigzag, up, down, you have maximized angles, which is the most stable configuration. And then of course, as you begin to twist and turn those sigma bonds, you can do so and not break any bonds. There's still 5 carbons all attached in a row, except now all of a sudden with these twistings, you've created steric hindrance. This would be the least stable configuration due to the very much crowding of the carbons in carbon 1 to 5. These become too near each other. Remember, there's hydrogens coming off as well, and that makes it very unstable. Draw skeletal structures for each compound, maximizing our bond angle. So just a practice to go from a condensed structure to a skeletal structure. When we see this prefix hex, we know that hex represents the prefix for 6 carbons in a row. Skeleton structure is also called a bond line structure, just so we're familiar with both terms. Remember that the point of any line and the intersection of any line represents a carbon. 1, 2, 3, 4, 5, 6 carbons. I just drew the bond line structure for hexane. Let's draw the bond line structure for heptane. Here the prefix hept means 7. We have 1 carbon at the terminal end with the CH3, 5 more carbons all containing CH2, plus 1 more at the end with a terminal CH3. That gives us a total of 7. 1, 2, 3, 4, 5, 6, 7. I've drawn the line structure for the compound heptane. If we wanted to convert skeletal structures to the complete structure with all atoms and bond lines. Now when I say complete, think of that as the Lewis dot structure. Alrighty, so we have 1, 2, 3, 4, 5 carbons in a row. And for Lewis dot structures, we really aren't concerned about proper angles. We're just getting connectivity in all hydrogens, and if there's any lone pairs, we would put those on the heteroatoms. We just placed 5 carbons in a row. Remember to complete their octet. They all require 4 bonds. So to do so, we imply that the hydrogens, even though they're not drawn in the line structure, we indeed do know that they're there. So here is the Lewis dot structure, the complete structure with all the atoms and bond lines drawn. This is a molecule called pentane. We have 5 carbons in the backbone. Here's a structure, 1, 2, 3, 4, 5 carbons in the longest chain, and at carbon number 3 there's a branch that contains 1 more carbon, a methyl group. So again, I'll place my 5 carbons in a row. There's the backbone, and I know at carbon 3 there's a branch leading down to another carbon. Now complete the octet of every carbon so that each carbon has 4 bonds, and that will give you insight into how many hydrogens it should have. Each terminal end receives 3 hydrogens to complete its octet. The interior carbons then get filled with the hydrogens as well. And don't forget down here, this carbon requires 4 bonds as well. Now, how does this sound for naming? Again, I haven't taught this lesson yet, but I'm just kind of seeding as much as I can so when we get there, it goes easy. The longest carbon chain is a pentane, 5 carbons. At carbon number 3, we see a branch that's 1 carbon long. At carbon number 3, the branched carbon will be named methyl since it's 1 carbon. And the backbone is still 5 carbons. We just drew 3-methyl pentane. And how about letter C? Letter C, I have 1, 2, 3, 4, 5 carbons in a cyclic structure. So that's that part. Off of this carbon, we see 1, 2, 3 more carbons. I'm just kind of giving you that backbone of what it looks like. Now just fill the octets. This carbon is at the terminal end. It will require 3 hydrogens to complete its octet. This carbon is bonded to 2 other carbons, therefore 2 more bonds are needed for hydrogen. This carbon is also bonded to 2 carbons, therefore 2 more hydrogens to complete its octet. This carbon is a tertiary carbon, so only 1 more hydrogen, and each carbon in the cyclic structure receives 2 more hydrogens. So this is allowing us to practice interpreting bond line formulas or skeletal structures and coming up with what that 3-dimensional look for that molecule looks like. All right, so what would this look like for a name? We had a cyclopentane, and again, coming up in a very close lesson yet, the 5 carbon member, 1, 2, 3, 4, 5 carbons in that cyclic structure. I'm going to let you know there's 5 carbons, all single bonds, but in a cyclic structure by saying cyclopentane. And what else? There's a branch coming off. A branch that's 3 carbons long. 3 carbons gets the prefix prop, and instead of naming it propane, because it's a branch, we name it propyl, just like we did over here, not methane, but because it's a branch, a substituent group, we name it methyl. Now this is all one word. It didn't come out just looking like that. It's propyl cyclohexane, all one word. And you know what else I might as well throw in here? We do not need the number 1 in this particular structure. It's not necessary because it's a cyclic structure. I already know that no matter what carbon I put that branch on, it will be called carbon 1 because every substituent needs to have the lowest number possible. So we'll just call it propyl cyclopentane. And we drew the complete structure and seeded the next lesson of naming it. Which two representations are identical and what is different? It's kind of like that Sesame Street game. What's the same and what's different? So here, the strategy is really kind of just seeding how we name compounds. I want you to work to find the longest carbon chain and number them. The longest carbon chain. Here's one. 1, 2, 3, 4, 5, 6, 7 carbons long. 1, 2, 3, 4, 5, 6, 7 carbons long. I don't know why that went straight. 1, 2, 3, 4, 5, 6, 7 carbons long. Even though A and B are bent, there's still 7 carbons. How about letter C? Find the longest carbon chain. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7 carbons long. Let's number those to make sure we see the difference. 7 carbons in the longest carbon chain. At carbon number 3, we have a 1 carbon branch, 3-methyl-heptane. Hear that prefix for 7? 3-methyl-heptane. At carbon number 3, there's a 1 carbon branch. The branch is now known as a substituent group. 1 carbon gets the prefix meth on a 7 carbon backbone, 3-methyl-heptane. I'm going to count again to make sure the substituent gets the lowest number possible. At carbon number 3, I have a 1 carbon branch. This is also called 3-methyl-heptane. A and B are indeed identical compounds. Even though they're twisted differently, they're the same compound. Single bonds can twist anyway. I'm going to number this 1, 2, 3, 4, 5, 6, 7. I'm going to number going the opposite way as well, just to make sure that branch has the lowest number possible. Yep, and no matter which direction I numbered, left to right or right to left, that branch comes out on carbon 4. So this name will be on carbon 4, 4-methyl-heptane, because the backbone is still 7 carbons long. So that branch is located on a different carbon. So letter A and B are indeed the same compound, and letter C is a constitutional isomer of A and B. It is a different compound. Well, we've been practicing section 3 all times long. It's time to just dive in and say, let's learn how to name alkanes. And the system we use for naming throughout the entire course, and it's the same system you used in the first semester for inorganic molecules. Organic molecules follow the same set of rules from IUPAC, the International Union of Pure and Applied Chemistry. It provides us a systematic way of naming organic molecules. So this systematic way of naming organic molecules makes sure that each compound gets a unique and unambiguous name. A unique and unambiguous means when I read that name, I can clearly draw its structure, and that structure is unique to its name from any other compound ever invented. For example, kind of giving us an application, most drugs, for instance, have 3 different names. The first of those 3 names is its systematic name. These are the long names you see on the back of a label. Let's say, for example, on the back of some Motrin or Advil, any type of acetaminophen, any type of anti-inflammatory drug. Its IUPAC name, for example, 2-4 bracket 4- parenthesis 2-methylpropyl phenyl propanoic acid. All of those key terms are giving me insight into the into the structure. In other words, I see a phenyl substituent group. I know that that eventually we'll learn is an aromatic ring, the aromatic ring called benzene. I know a methyl group has 1 carbon. I know a propyl group has 3 carbons. And I can tell where they're located by the number provided as a locant. The location of those methyl groups and the propyl group are given to me with those numbers. I also see propanoic acid. This oic acid, we will learn 3 carbons for prop, and we'll learn that that represents the carboxylic acid functional group. We don't know that yet, but I can give insight into this particular compound, kind of looking at its systematic or IUPAC name. You then find a generic name, which is the official, internationally approved name of the drug. For example, ibuprofen. So that in the trade world, we will hear it as Motrin or Advil, coming from the actual company that manufactures the drug. So Bayer, for example, might be manufacturing Motrin under the generic name ibuprofen, under the systematic name of 2,4,2-methylpropylphenyl propanoic acid. Give you an idea of what that means. Here is a box labeled as Motrin. That's its trade name. We can see that it has a generic name there called ibuprofen, and the manufacturer is usually typically given on that as well. And then the systematic name leads us to this structure. Here's that functional group, carboxylic acid, coming from this part of the name. Here's that aromatic compound that we said phenyl. We can see that there's 2 methyl groups coming off of a propyl group and the longest carbon chain, 1, 2, 3. So here's a methyl, and I can see that 2,4-methyl part, and I also see that there's a propyl group part of this name. That's where we're heading, is kind of making sure that every organic molecule has a unique name. So, the names of alkanes with substituents have 3 parts. We said it has a parent name, and that parent name comes from the longest continuous carbon chain: methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane. Those would be the parent names of carbons 1 through 10 in the backbone. We know that the suffix for our alkane family is the ane ending, but that suffix will change as we move through the course and introduce other functional groups. And a prefix to tell us the location, identity, and number of any substituents attached to that carbon chain. We have a prefix, we have a parent, and we have a suffix. The prefix tells us what and where are the substituents. These are the branches, if you like that word better. What is the longest carbon chain? That comes the parent, meth, eth, prop, bute, and so forth. And the suffix tells us the functional group. And in this chapter, the suffix will always be ane, since we're studying alkanes, but that will change as we progress through our lessons. So carbon substituents are called alkyl groups. Alkyl groups are formed by taking the parent chain and removing 1 hydrogen. So for instance, if I have a methane, which is CH4, and it becomes a substituent group, it now removes 1 hydrogen, and in doing so, it gives it a space for bonding to the parent chain. So we remove a hydrogen and use that 4th bond to attach it to the longer carbon chain so that the branch has a way of attaching. To name the alkyl group, instead of saying methane, you use the YL ending and it becomes methyl. METHYL for a 1 carbon branch. So the alkyl group gets named methyl, ethyl, propyl, butyl, and so forth. Each alkyl group has a bond that can be then attached to something else, which is typically the parent chain when we're looking at alkanes. Removing one hydrogen from methane gives us methyl. Removing one hydrogen from ethane gives us ethyl. So we can begin to hear how these substituent names are going to start sounding. If the parent chain has one carbon, the structure is CH3, then a dash. This dash represents the line that's going to bond to the parent chain. We hear that named methyl. So the structure, CH3 dash, the name methyl. If we have two carbons in the substituent group, you notice CH3, CH2 dash, where that dash represents the bond back to the parent chain, and you'll hear it called ethyl. If there are three carbons in the branch, CH3, CH2, CH2, then a dash, that dash will represent the bond that goes to the parent chain, you'll hear it called propyl, and keep going. 4 carbons in the chain followed by a dash represents 4 carbons, butyl. If you see 5 carbons, we go back 1, 2, 3, 4, 5 carbons and then a dashed line to represent the bond going back to the parent. That's a pentyl. And of course we'll end here with hexyl, 6 carbons in a row ending with a dash to represent the bond going back to the parent chain, which would be called hexyl. So the alkyl group, these are substituent groups, meaning the branches that come off of the parent chain. Here we have, as an example here, notice that this branch coming off a cyclohexane, this cyclohexane has 6 carbons all in one structure. They're a cyclohexane. So we would call this methyl cyclohexane. Here is an ethyl group. Notice that it's 2 carbons long. We don't need a locant here, a number, because we know in a cyclic structure the first carbon will always contain the substituent group. So this would be called ethyl cyclopentane. And here we have 1, 2, 3, 4 carbons in that group, which is called butyl. So this would be called butyl cyclohexane, since it has 6 carbons in its membered ring. The longest carbon chain in the cyclic structure gives the prefix hex for 6. So we're going to dive in and start practicing. Step 1, find the parent carbon chain and add the suffix. And the key here is finding the longest continuous carbon chain and ending it with the ANE ending. So the challenge as you begin naming is to find the longest carbon chain. Now in this example provided, you don't have to draw this, but we can see 1, 2, 3, 4, 5, 6 carbons in the longest carbon chain. But I want you to know that it doesn't necessarily have to be in the same straight chain. You get 6 carbons going in this direction as well. So finding the longest carbon chain challenges you to look in all directions to find that chain. Find the longest carbon chain and that becomes your root word, the backbone name. The longest carbon chain could be written horizontally. It could have branches. It doesn't matter. It just has to have the longest chain. As I said, I can go straight across and get 6 carbons. I can branch down because they're still connected to each other. And I can zigzag. I just want to make sure I'm finding the longest chain where one carbon bonds to the next, bonds to the next. Step 2, number the atoms in the carbon chain to give the first substituent the lowest number possible. So if I'm looking at a 6 carbon chain and I notice that there's a branch at carbon 2, it is correct to name that 2-methylhexane. It is incorrect to name it 5-methylhexane. The branching must have the lowest number possible. You may sometimes number from left to right to achieve that, and sometimes you number right to left to achieve that. But the goal is to find the longest carbon chain and number it to give any branching the lowest number possible. And the third step says, name and number the substituents. So you're going to name the substituents as alkyl groups, for example, methyl. And then tell me the location by using a number. The number designates where it's located on the backbone chain. And when we put that all together, we come up with a numbering system and a naming system that's unique for every molecule. Remember that every carbon belongs to either the backbone chain, the longest chain I'm calling the backbone, or it belongs to a substituent, but it never belongs to both. Every substituent needs its own number, and I don't care if it's the identical number as something you've used already. It has to have its own number. If you're naming two or more substituents that are the same, use prefixes to tell me how many there are. For instance, if I have two groups that are the same, the prefix I use is di. If I have three groups that are the same, the prefix I use will be tri. For 4, it's tetra, and so forth. 2,2-dimethyl, 2,2,3-trimethyl, 2,3,4-trimethyl, and so forth. I'm letting you know the location of each substituent with a number, and if those substituents are identical, I'll let you know by a prefix. The following compounds contain 2 methyl groups, so we use the name dimethyl to locate them, just as an example of that previous slide. Locating carbon 3 is a methyl. Locating on carbon 2 is a methyl. So I'm going to tell you at carbon 2 and 3 are methyl groups. We hear that 2,3 dash dimethyl, and of course the parent chain is 6 carbons long, so we hear hexane. All one word, 2,3 dimethylhexane. We're going to combine the substituent names with their numbers, add the parent, and finally the suffix. If there's more than one type of substituent, we alphabetize them, ignoring any prefixes. So for example, if I have an ethyl, which is 2 carbons, and a methyl, which is 3 carbons, and a propyl, which is 3 carbons, this is 2, 1, 3. I might have misspoke. The order in which we list them is not based on the number of carbons, but it's the alphabet. So here, ethyl would come before methyl, which comes before propyl, just looking at the alphabet. However, if I had the term dimethyl and another one that had ethyl, I do not use the prefix in alphabetizing. I still go by the root word here, ethyl and methyl. Precede the name of each substituent by the number. Remember that there has to be one number for each of the substituents. Separate numbers by commas and separate the numbers from the letters by dashes. Separate numbers by commas. Separate the number from the letters with a dash. Are you ready to try some? If you're ready to try some, pause the video and do the Let's Practice on page 9. Practice naming those compounds and come back when you're ready to check your answers. Give the IUPAC name for, trying to get to the structure, here it is. Here's problem 12.4. Let's practice. Give the IUPAC name for the following compound. Try just this one. Pause the video a moment, give it a name, and let's come back to check. I'm so proud of you for not cheating. Pausing the video and working on it yourself is so critical to the learning process. If you're listening to my voice now, it means you've paused and you've come back to check. So our first challenge is finding the longest possible carbon chain, and that just takes some diving in and figuring out where should I start. Here I have carbon 1, 2, 3, 4, 5, 6, 7, 8. For no other reason than I have to pick a variety of ways, I'm going to just start going left to right, straight across, and see what I get. I come up with 8 carbons going straight across. Is there anything longer? 1, 2, if I go up, I'm done, so no there. 3, 4, 5. What if I go up 6, 7? Well, 8 is longer than 7, so that didn't work. One more try. How about 1, 2, 3, 4, 5, 6, and instead of going across, let's go down. Oh, that also gives me 7. So with this example, the longest chain we found was just straight across. And so I'm just going to clean that up and give us that longest chain at carbon 1, 2, 3, 4, 5, 6, 7, 8. Since the longest chain was 8 carbons, we now know the backbone root word of this name. Since it's 8 carbons long, it gets the prefix oct to represent 8. Since we're in the alkane family, these are all single bonds. The last suffix there is ane. So that's going to be the last part of the name, octane. Now, we want to start figuring out the substituent branches. Where do we see branching occur? So I see a branch here, a CH3 group. I see a branch here, CH2, CH3, and I see another branch down here at carbon 6, CH3. By the way, one of the things I want to really highlight is, did we number the correct direction? So for instance, if I had numbered 1, 2, 3, 4, 5, 6, 7, 8, going from right to left instead of left to right, the first carbon that we see going right to left is carbon 3 that gives me a branch. So carbon 3 is the first that branches to a substituent group. If I number from left to right, the first carbon I see going left to right is at carbon 2. I see something branching there. So what is the correct way to number this structure? Right to left or left to right? Well, the secret lies in making sure all substituents have the lowest number possible. You want to number this chain so that you hit the branch at the lowest number. The first branch has to be the lowest number, and that happens to be from left to right. So this time, I'm going to start numbering from left to right. Now let's name these. At carbon 6, I see a 1 carbon branch called a methyl. At carbon 5, I see a 2 carbon branch, so it will be called an ethyl. And at carbon 2, we have a methyl. There's no other branching other than what I've highlighted in blue. Now, remember when we name these, we alphabetize the branches. Alphabetize the branches. Ethyl comes before methyl in the alphabet. So at carbon 5, we have an ethyl group. Separate numbers and letters by dashes. 5-ethyl. At carbon 2, comma, and 6, separate numbers by commas. Separate numbers from letters with dashes. We see 2 methyl groups. Emphasize that we do not use the prefix di when alphabetizing. E becomes the first in this name because it's before an M in the alphabet. Don't use di, tri, and so forth when you're alphabetizing. Do not separate letters in the name. You just keep going. We said that the last name would be octene. 5-ethyl 2,6-dimethyl octane is the name of that hydrocarbon. How'd you do? Once we get the rules down, this becomes simplistic. Step by step, we went through our answer and we found 5-ethyl 2,6-dimethyl octane. Excellent work. How about some more? Please pause, give yourself some time. What I'm going to ask that you do is just pause this video and you're going to practice naming page 9, page 10, page 11, and stop where it says 12.5 cycloalkanes. Pause the video, give yourself time to work, and come back to check your work when you've completed and want to get some feedback. Okay, you're back, so that means you've been working hard. Let's see how it paid off. We want to find the longest carbon chain. I'm going to number right to left, and I'll number left to right. And I get the same numbering system either way. At carbon 3, I have a branch. That branch, I'm noticing, is this methyl group. That's the branch in a 5-carbon chain. So it doesn't matter which way I number in this particular example because either direction gives me the substituent group at carbon 3. At carbon number 3, we have a methyl group. Remember, separate numbers and letters by dashes. 3-methyl, the backbone is 5 carbons, so this is pentane. 3-methyl pentane. Letter B, find the longest carbon chain. Let's just dive in and see. 1, 2, 3, 4, 5, 6, 7, 8, 9, if I number from left to right. 1, 2, 3, 4. I won't go up because that's the terminal chain. I'll go 5. What if I go up? 6, 7, 8. Well, that's not longer than 9, so that's not the correct direction. How about 1, 2, 3, 4, 5, 6, 7, 8, 9. How do I know if I go left to right or right to left? Well, that answer is, where does the first branch occur? We want the substituents to have the lowest possible numbers. If I numbered from left to right, the branches become carbon 4 and carbon 5. If I numbered from right to left, the branches become 5, 6. So clearly I see that 4, 5 is the lowest numbering possible. So after checking that, I know I'm going to number left to right. All right, so let's name these. Carbon 4 is a 1-carbon branch, so that's a methyl group. Here is a 1, 2, 3 carbon branch. 3 carbons gets the prefix prop, so this is a propyl group. And it's the only branches that I see in letter B. Now remember, we're going to alphabetize, not based on the number, but based on the alphabet, methyl and propyl. Methyl is first in the alphabet. So I tell you at carbon 4, there is a methyl group. Separate numbers and letters by a dash. At carbon 5, there is a propyl group. Separate the number and letters by a dash. letters do not get separated from one another. So this simply becomes propylnonane is the backbone for 9 carbons, all one word. 4-methyl 5-propylnonane. How you doing? These become fun. All right, so let's try the next, letter C, finding the longest carbon chain. Well, the longest chain is not this guy, he's in the middle. So let's count 1, 2, 3, then I go this way, 4, 5. If I go down, I'm done. If I go over, I'm done. So it doesn't matter if I go down or over. That's still 6 carbons in a row. 6 carbons in a row. And I can see that I have branching with a methyl here and a methyl here. Now, is that the proper way to number that? The way I have it listed, I have a methyl at carbon 3 and another one at 5. Let's see if I had done carbon 1, 2, 3, 4, 5, 6. If I numbered right to left, where do my substituents end up? Well, they end up at carbon 2 and again at carbon 4. 2 and 4 is a lower numbering system than 3 and 5. So this time I must number from right to left to get the substituents the lowest possible number. Let's put it together. At carbon number 2 and at carbon number 4, 2, 4, remember commas separate numbers, dashes separate numbers from letters. 2, 4, I have 2 methyl groups, so we label that as dimethyl. The longest carbon chain for the backbone contains 6 carbons. That's hex. This is called 2,4-dimethylhexane. You just read that, 2,4-dimethylhexane. You want to keep going with me. Let's keep practicing. How many carbons are in the longest carbon chain? Well, I can count 1, 2, 3, 4, 5, 6, 7. Going straight across right to left, I get a methyl group coming off of carbon 2. If I had numbered left to right, the first branch wouldn't come off until carbon 3. The longest carbon chain I'm finding is 7 carbons long. At carbon 2 and at carbon 5, I have 2 methyl groups, so I use the prefix di to let you know they're identical groups. 2,5-dimethylheptane to let you know there's 7 carbons in the longest carbon chain. Letter B might be helpful if we drew out from the condensed formula to the structural formula. Let's focus on this carbon. That carbon has 2 methyl groups coming off of its branching. Notice how it has 2 methyls and 1 hydrogen. So that's what it means by CH3 taken twice. CH. That carbon has 3 of its 4 bonds taken care of. Then we see CH2 taken 3 times. That means we're going to have 3 carbons in a row. The CH2 is telling us that those bonds are hydrogens. Right? So CH3, CH3, CH, CH2, 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 and then we see the terminal end, CH3. So now that I've taken the condensed formula and drew out its, what I would say its structural formula, we can start counting. At 1, 2, 3, 4, 5, 6 carbons in the longest carbon chain. At carbon number 2, there's a branch. It's 1 carbon long, so it's a methyl alkyl group. The prefix 6 gets hex. This is ane, 2-methylhexane. Letter C, 1, 2, 3, 4, 5, 6, 7, 8, 9 in the longest branch. So I know that it will be nonane. Known is the prefix for 9. Now, did I number correctly? If I went this other direction, the first branch occurs at carbon 4. And so if I wrote it in blue, my commas, my locants there, the numbers to tell me where the branches are would be 4, 7. Numbering from left to right, it looks like 3, 6. Right? Carbon 3 and carbon 6. So that's the lowest possible numbering system. So indeed, we want to number from left to right. So we would say, I'm going to just make sure we have this all written in one word, 3, 6. There are 2 methyl groups on a 9 carbon chain. 3, 6, dimethyl, no name. Letter D. At letter D, I'm finding the longest chain to be 7 carbons long. If I check and numbered the opposite direction, the locant there for the branch of methyl would be at carbon 5. If I numbered from left to right, I get a 5. If I number from top to bottom, starting up here in purple, the locant becomes a 3. So that's the winner. We want the branch to have the lowest number possible. So at carbon number 3, we have an alkyl group, 1 carbon long, so that's methyl. And the longest carbon chain is 7. So that's 3-methylheptane. Are you on a roll? You've got more. Because repetition is our friend while we're learning. There's just no way of getting around it. Letter A, I recommend drawing out so you can see the branching. Focus on this carbon first, after the parentheses. That carbon is telling me it has 2 other carbons, CH3s, that are attached to it. See that CH3 taken twice? Attached to that carbon. The 4th bond leads to the next carbon. And that tells us there's 2 more hydrogens, or I'm sorry, 2 more methyl groups and a hydrogen. See how this really helps in determining the longest carbon chain. What I've highlighted in yellow is this carbon. That's this carbon. It has 2 methyl groups and a hydrogen. What I'll highlight in blue is this carbon. It also has 2 methyl groups and a hydrogen. So seeing it drawn out from its condensed formula into a structural formula helps us count. Now we can see the longest carbon chain. 1, 2, 3, 4 carbons long. And I can get that from a variety of ways. 1, 2, 3, 4. That's still correct. At carbon number 2 and at carbon number 3, we have a methyl. In a 4 carbon chain, so that's called butane. 2,3-dimethyl butane. How about letter B? Now what's nice is B has it all drawn out for us, so I don't have to redraw anything. We just want to work to find the longest carbon chain. I just think at first glance, I'm unsure where the branching will be the lowest. I got to try both ways. 1, 2, 3, 4. That's not a branch, is it? It's just directly leading me to the next carbon. 5, 6, 7. Now that's a branch. 8, 9, 10. Can I get that lower by numbering in a different direction? Most likely. Let's try that out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And certainly I did. The branching occurs at carbon 4 when I numbered with the red system going left to right. And the only substituent, the only branching I see is occurring here. The rest of all those carbons are part of the backbone, aren't they? And so when I number, the backbone is 10, so that's decane. And at carbon 4 is a 2 carbon unit, so it gets a ethyl. So at carbon 4, there is an ethyl group. Notice that numbers and letters are separated by dashes. So 4-ethyl, but don't separate letters. Just keep going as all one word. Decane. And one more, letter C. It looks like I'm going to start numbering from right to left. Just on a hunch, I might find the longest chain right to left with the lowest number of branching. So I count 8 carbons numbering right to left, with the branching occurring in the following areas. I have an ethyl group at carbon 2, and that's carbon 3, sorry, and again another methyl group at carbon 4, and an ethyl group also at carbon 4. All right, so let's put it together. Alphabetize the substituents. In the alphabet, ethyl comes before methyl. And I know that the prefix di does not get used when I alphabetize. At carbon 4, there was an ethyl group. At carbon 3 and carbon 4 are methyl groups. And the backbone had 8 carbons called octane. 4-ethyl, 3, 4, dimethyl octane. A+ so far, I bet, aren't you? Doing great work. I want to keep cheering you on because there are a lot of practices. The only way to get proficient is to continuously practice. Now we're going to work from line structures. We got to work through to find the longest carbon chain using line structures and then try to name them. So I just recommend diving in. Let's see. I'm going to just start counting for no other reason. I have to pick a place. 1, 2, 3. If I go up, the longest chain I have is 6 carbons. What if I go 1, 2, 3 and go continuously over 4, 5, 6? I can find 6 carbons. 1, 2, 3, 4, 5, 6. Anything else you want to try? 1, 2, 3, 4, 5, 6, 7. Oh boy, I found something longer, which I kind of suspected because I had 6s coming 2 ways. How do I choose? I had to have found something longer. If I have to choose, I want the one with most branches. But now I found a 7. Let me kind of clean this up. I can find a 7 by going 1, 2, 3, 4, not down because that stops at 6, but up. 5, 6, 7 is the longest carbon chain. And I like the way that that numbered because I'm seeing that in terms of groups, carbon number 2 will give us a methyl. Carbon number 3 gives us an ethyl as well, 1 carbon. 5 gives us the same. And here I have a 2 carbon branch. Whoops. I just wanted to make you see that that's a 2 carbon branch. Now we go to work naming it. So the parent name I know will be heptane. I can see at carbon, at carbon 2, 3, and 5 are methyl groups. And I see at carbon 4 is an ethyl group. So those are the 3 parts of our name. We have a backbone of heptane. We have a total of 3 methyl groups located at carbons 2, 3, and 5. And we have an ethyl group located at carbon 4. Let's alphabetize the substituents and put it all together for a final answer. Ethyl comes first in the alphabet from methyl. Disregard the prefix tri. So 4-ethyl dash 2, 3, 5 trimethyl heptane. You did it. That was a good one. The next set, find the longest carbon chain. 1, 2, 3, 4, 5. Did you find anything longer? Even if I started down here. 1, 2, 3, 4, 5. That's identical. No difference there. Starting from the top or from the side there, I get 5 carbons. So I'm just going to choose, let's go right to left. I had a couple of choices. They're the same. 1, 2, 3, 4, 5. Now with this, I have 2 identical substituents. I have a methyl group here and here. So I don't have to worry about alphabetizing. What I'm doing is saying at carbon 2 and 3, there are methyls on a 5 carbon chain. All right, one more in this set. Let's find that longest carbon chain. 1, 2, 3, 4, 5, 6, 7, 8 carbons. Can you find anything longer? I'm going to try numbering this way. 6, 7. So nope, keep going. 7. Now the reason I checked that was to compare where I saw that first branch. 4 versus 5. Well, 4 is a smaller number than 5, so I do need to number from bottom up. At carbon number 4, there is a 2 carbon branch and an 8 carbon backbone. 4-ethyl octane is the name of that compound. Give the structure for the following IUPAC name. Give the structure for the following name. All right, so now I'm going to read it and kind of put it together. 2,3,3 trimethyl pentane. Go here first. How many carbons are in the backbone? And there's 5. So I'm just going to get kind of my connectivity figured out first. There's 5 carbons in the backbone. 1, 2, 3, 4, 5. At carbon number 2, there's a methyl group. At carbon number 3, there happens to be 2 methyl groups. 2,3,3 trimethyl pentane. Now what does that look like? In a backbone of 5 carbons, 1, 2, 3, 4, 5. So there's the backbone in that zigzag fashion. Carbon number 2 has a methyl group, so I'm going to make a branch. Carbon number 3 has 2 methyl groups, so that gives me 2 branches at carbon 3. And that's the line structure for 2,3,3 trimethyl pentane. Let's keep practicing that same skill. 3-methyl hexane. All right, so the prefix is hex. 1, 2, 3, 4, 5, 6, and at carbon 3 is a methyl. So I just get my connectivity figured out first. Then I can do the structure. 1, 2, 3, 4, 5, 6 carbons in the zigzag fashion, and at carbon number 3 is a methyl group. Notice that it is absolutely okay. 1, 2, 3, 4, 5, 6. 1, 2, 3. If you put your methyl there, that is exactly the same structure. At carbon number 3, there's a methyl in either direction. Both are the same structure. How about number 2? 3,3-dimethyl pentane tells me there's 5 carbons in the backbone, pentane. And at carbon 3, there's a couple of methanes there. So that's kind of its rough draft. 1, 2, 3, 4, 5 carbons in a zigzag pattern. At carbon number 3 are 2 methyl groups coming out. There's the line structure for 3,3-dimethyl pentane. Carbon 3, or I'm sorry, number 3, 3,5,5 trimethyl octane. So I'm going to just draw 1, 2, 3, 4, 5, 6, 7, 8 carbons is the octane part of that root word. At carbon number 3, There we go. Carbon 3, we have a methyl group. So I'm just going to create a line. There's a methyl. And carbon 5 are 2 more methyls. So I'm going to put 2 more methyls down at carbon 5. What's another way of drawing that? 1, 2, 3, 4, 5, 6, 7, 8. What if I numbered this direction? At carbon number 3 is a methyl, and at carbon number 5 are 2 more methyls. These are the same structure. I can number them right to left or left to right. It does not matter. You have the same compound. And number 4, I have room up here. Hexane is the root word. 1, 2, 3, 4, 5, 6. 6 in a row for hexane. Let's number it. 3 ethyl, 4 methyl, hexane. So at carbon 3 is an ethyl group. That's 1, 2 carbons coming off of that. So it's a branch of 2 carbons. At carbon number 4 is a methyl group. So that's a 1 carbon branch. Number it the other direction. 1, 2, 3, 4, 5, 6. If carbon number 3, 1, 2, 3, has an ethyl group, carbon number 4 has a methyl group. If I number the opposite direction, it's the exact same structure. So I'm emphasizing they're not different, they're just numbered. It's like taking the molecule and just flipping it over on the page. You're doing such good work. Let's pause the video here, and next time we pick up, we'll practice naming cycloalkanes, very similar to what we've just been doing, but putting a new prefix in cyclo to represent a cyclic structure.